Here's an example. There are two cars driving along perpendicular streets. One is going east and the other is going north from a particular intersection. So here's this intersection, and we have one car that's going east. Here's my terrible car, or my very artistic car. Here, he's going that way. And then I have another car that's going north. And try to pretend to draw this. Oop, whoa, whoa. There's my car. Okay, so I got two cars driving. The first car is traveling at 30 feet per second away from the intersection. The second car is traveling at 20 feet per second away from the intersection. And we want to find the rate of change of the distance between the two cars after 4 seconds. So what I'm going to do is I'm going to call this X and I'm going to call this Y. Okay, so this car is going in the X direction, this car is going in the Y direction, and I'm trying to find about the distance between the cars. So the distance between the cars, I'm going to draw a dotted line to represent that. That's like here. I'm going to call that side Z. So what we really have here is a triangle that we've drawn, and we need to figure out, first of all, what type of equation we're going to use. So I need to use the three sides because I know something about X, I know something about Y, and I had to figure out something with Z. So I'm going to use Pythagorean theorem here. So my equation that I'm going to work with is X squared plus Y squared equals Z squared. So that's like my formula. Now I want to figure out the information. So I have one car that's going east, so that's car X. So the first car is traveling 30 feet per second away from the intersection. So that's car X. So the first car, we're going to call that dx over dt. So the derivative of x, which is the direction that car is going, with respect to time, that's going to be 30 feet per second. Then I have the second car is traveling 20 feet per second away from the intersection. So that's y. So we'll say dy over dt is equal to 20 feet per second. And we want to find the rate of change of the distance between the two cars. So we want to find dz over dt equals question mark. That's what we're trying to find. And we're trying to figure it out when after 4 seconds. So when t is equal to 4. So I'm just going to underline 4 seconds and we'll come back to that. So what I have to do is I have to take the derivative of this with respect to time. So I've got the derivative of x squared, so that's going to be 2x dx over dt plus 2y dy over dt equals 2z dz over dt. So we can see that all of these have 2's that they are divisible by. So what I can do is divide everything by 2. So I end up with a simpler equation. So I have x dx over dt plus y dy over dt equals z dz over dt. Okay, and I'm just going to circle this because this is what we're going to be kind of using. Okay, this one's a little bit trickier because there's kind of another step that we need to figure out. So if I wanted to plug in my information, dx over dt I know is 30, so I can plug that in and I can plug dy over dt. The dz over dt is what I'm solving for, but I also don't know x, y, and z. So let's recreate my triangle over here. Okay, so the x direction car is traveling 30 feet per second away from the intersection. That's the car's rate. So the car's rate is 30 feet per second, and we're trying to figure out the distance after 4 seconds. So if the car is traveling 30 feet per second, after 4 seconds, car X is going 120 feet. Okay, and I got that because I did 30 feet per second times 4 seconds. Okay, so that's where I'm getting the 120 from. I'm going to do the same thing for y. So car Y is traveling at 20 feet per second, so that's the car's rate, and it's traveling for 4 seconds again, so 20 times 4 is going to give me 80 feet, and that's how far car Y went. So by using Pythagorean theorem, I can figure out what side Z is going to be. So Pythagorean theorem, we've got so x squared, so we're going to do like 120 squared plus 80 squared equals z squared. And if we solve this correctly, we get that z is going to be equal to 144.22. So that's like an estimation, right? I get plus or minus, but negative wouldn't make sense in this case since it's talking about a distance, which is in feet. So now what I can do is plug in all of my information. So in place of x, I'm going to use 120. So I'll have 120 times dx over dt, which is 30, plus y, which is 80, times dy over dt, which is 20, and that's equal to z, which is 144.22, times dz over dt, which is what we're solving for. Okay, and if you multiply everything and then divide the 144.22, we should get that dz over dt is equal to 36.056 feet per second. Okay, and then let's look at this last example. So a cylindrical tank with a radius 5 meters is being filled with water. So let's draw a very bad cylinder here. Okay, there's my cylinder. The radius is 5 meters, so I'm going to, here's my radius, and it's being filled with water at a rate of 3 meters cubed per minute. So like there's some type of like water in here that's being filled. How fast is the height of the water increasing? So first things first, figure out what shape we're using. It's cylindrical, so we're using a cylinder. We know that the volume of a cylinder is going to be pi r squared h. Okay, and they told us that r is equal to 5. And it's being filled with water, so the rate of the volume, so dV over dt, is going to be 3 meters cubed per minute. And we want to find how fast is the height of the water increasing. So we're trying to find dH over dt. So we need to take the derivative with respect to time of the entire equation. So we'll get dV over dt is equal to, so pi r squared h, we have to use the product rule. So pi r squared would be our first and h would be our second. So first, which is pi r squared, times the derivative of h, which would be dh over dt, plus the second, which is h, times the derivative of the first, which would be 2 pi, I'll just tack on the r over here, dr over dt. Okay, so now we're going to plug in things we know. So if we look at this, we know r, because it's 5. dH over dt is what we're trying to find. We know dV over dt, but we have a problem over here. We don't know h, and we don't know dr over dt. But let's think about this. If we have a cylinder, right, if you have the radius of the cylinder, which is 5, if I take the radius at any point within this cylinder, the radius is not changing. It's going to be 5. If I take the radius down here, that's also going to be 5. The shape has a constant radius no matter how full the cylinder is. So since the radius is not changing ever, then we know that dr over dt, which is the rate of change of the radius, is equal to 0. So when it's a constant, like 5, it's not going to change at all. So other shapes, the radius may change depending on where you're looking at the radius, and in future examples, we'll see when that happens. But when you have a cylinder, you have a constant radius. So dr over dt would be 0. So what's going to happen is it doesn't matter that we don't know what h is. That's going to be gone because dr over dt is really 0. So all we have now is dv over dt equals pi r squared dh over dt. So let's plug in what we know. dv over dt is 3. We got pi r squared, so I'll just put the 5 here, squared, and then dh over dt is what we're solving for. So I get 25 pi on this side, dh over dt, and I divide that out. So dh over dt is equal to 3 over 25 pi, and then the units here are going to be meters per minute. Okay, if the units are confusing you, you can keep the units with the numbers when you plug them in, and then you can see what the units will be. But most of the time, you can kind of just figure out what they're going to be and then tack them on at the end.